Okay, today we're going to do section 6.1. So, recapping some things about Algebra 1. In Algebra 1, we look at mainly three main models of functions, which are the linear, the exponential, and the quadratic. We have looked at and explored the linear and the exponential models already. Now we're going to look more on the quadratic. So, today I want to review some of what we looked at from data, from situations, and determine which type of model would best represent the data. Then we're going to find that model algebraically and with regression tools on our calculator. And I'll show you how to do all that kind of stuff. So the first one we're going to do is recap the linear model. Bring it all back together, showing the comparison between everything. So what do we know? If the data follows a linear model, what can I say? What do I know? Then we know that it must have a constant rate of change. A constant rate of change. Okay? Now, what else did we call this constant rate of change? Had other names too, one of which was called the slope. That was the constant rate of change. It's called the slope. And it had other names too. And when we talked about sequences, it was also called the common difference. So all these things refer to the same number that we found. Okay? So let's go back and look at one. In this lesson, they had another name to it, very similar to this one right here. So in this one, they're going to use what's called the first differences. The first differences. That's another name they're going to use for the same number that we have found in the past. Okay, so let's look at a real quick example of one that I pulled out. Here's x and y, and there's 1, 0, 1, and 2, and I'm going to give you these numbers here, 5 and 7. So showing how all these things are the same number here. Remember, when we have a table, we can show this is the change in the x's. This is +1. All these are +1. +1. Down here is +2. But I'm going to look at it a little bit differently. What I'm going to do is show you the common difference, which is we're going to take these two things, and it's that one minus that one. So 1 minus a -1. And that gives us a 2. 3 minus 1, 2. 5 minus 3, 2. And 7 minus 5, which is 2. And I'm showing you this way because it's the common difference. We saw that it's 2 each step. But in the first differences, this is kind of like how they're talking about it. So this right here, this 2 is your first difference. It's literally the same thing we've been doing. Now, the important part here is let's look at some of these other formats. What is it as a rate of change and as a slope? Remember that the slope is the change in the y values divided by the change in the x values. The change in the y values is 2. The change in the x values is 1. This gives us a slope rate of change that is 2. And the first difference and the common difference is literally the same thing. You subtract consecutive terms and you get the common difference. Okay? Now, something that's important to remember. Okay? And it's going to continue on through all these other ones. For this to work this way, all x values must be equally spaced. Okay? Equally spaced. So this is kind of an important concept here. I can't have this going by +1 and this by +2 because I have to be able to show that consecutive term aspect to get the first differences. Now, once I have this information, this common difference, this first difference I see, because this is a first difference, So that's what we're doing. Because that is the same number on all cases, that's what makes this a linear model. Okay, that's how you identify it. It's the first difference. It's the first difference is the same. Then you have a linear model, and you can use the point slope formula to find the equation. This is my slope. This is any point in here, so try and use the 0 point. That's the easiest one. Why is it going blurry? So we can plug in our numbers. Y minus 3 is 2 times x minus 0. And then we can solve this for y very easily and get 2x plus 3. So here is a linear model for this table. Okay, that's linear. Now let's look at the new one, quadratic, that we're going to look at a little bit more detail. And I'm doing quadratics because linear and quadratics are in the same family of called polynomials. So they are very similar in nature. This one is just one value higher. It's like a one, called a degree. It's 1 degree higher. And here's how this one works. So if the data follows a quadratic model, then what's called the second differences will be the same. So in a linear, the first differences were the same. In a quadratic, the second differences is the same. And that's how you can identify a table of values as if it's going to be quadratic. You just do the first and second differences. But if the second ones are the same, then you actually have a quadratic model. And then you can follow processes for finding that equation. So here's another one. And here's -2, -5. There's certain characteristics that you can kind of see in a table sometimes, depending on what number you have, and you'll see a certain pattern that will help you also indicate that it might be a quadratic model. So again, these all have to be equally spaced for this to work. This is all +1s. And then we do the first difference. If I subtract these two numbers, so it'll be a -5 minus a -2, I get -3. If I subtract those, -14 minus -5, and then I get -9. And because I'm running out of room in here, subtract those, I'm going to get negative, so I'll write it down here, -15. And if I subtract these two numbers right here, the difference then becomes -21. This is your first difference. There. So then we do the second difference is subtract these. So subtract those, you get a -9 minus a -3, and that gives me -6. -15 minus -9, and you can see that you're going to get -6. And in fact, all of these, -21 minus -15, also gives me -6. And so this is the second difference. And if the second difference is the same number, okay, then you know you have a quadratic model. And we're going to look as we go through this unit how to write equations in different models and stuff like that. So right now we're just learning to identify if I even have a quadratic model. Okay, so again, if the second differences is equal, the same number all the way, then you have the data in the table is a quadratic model. Now, for now, as I said, for now, we don't know how to find the model algebraically yet. We haven't really explored the actual forms of the models. So we're going to use our calculator to find the model, the quadratic model for this. Now, there is a video in your important info about how to use the calculator to do what's called a regression model. So we're going to use, at this stage, we're going to use the regression model. Let me put it differently. Let's use the regression tool on our calculator. And Desmos can do this also. You'll just have to watch a little YouTube video on how to do the regression model on your Desmos account. Okay? So I'll walk through this real quickly. And I'll show you how this works. But again, this video is in more detail and a lot slower. In that video, I walk you through it a little bit faster. Okay, so what first thing you do is you can put in, you go to the screen right here, you can put in some data. Again, I'm not explaining all the steps I'm doing. I'm just showing that you can do it in here. The A column right here is going to be all my X's. This is just a spreadsheet. And then we have -2. Oops. -2, -5. All right, so all the data is in there. And then I can go to menu. You can't really see it. Let me put it up here so you can see. Go to menu. And we go down here to statistics. One stack calculations. So we're going to do number 1. And then if you look down here, you see all these different regressions that are in here. And you can go down here and see that quadratic is sitting right there, quadratic regression. And it's going to give you a model equation and then the numbers to plug into that model. Okay, so this list right here is going to be the A list. This one is going to be the B list. And then you can just default all the rest. And so the model over here that you really can't see, but I'll write it out for you, is y equals ax squared plus bx plus c. And then it tells me what a, b, and c are. A is -3, b is 0, and c is -2. So my model for this equation up here is going to be y equals -3x squared. There's no b number, so that's a 0. And then there's going to be a -2. This is my model, okay, for that right over here. So if I plug this 3 into here, I'm going to get -29. If I plug in 2, 2 squared is 4. 4 times -3 is -12. -12 minus 2 is -14. It gives me the rule that I can follow. And then this number right here, we'll talk about it later date. The closer that number right there is to 1, the better your model is. We have a perfect model. This is the exact model, and we're good to go. So that is how I can use the calculator. We will talk more about that as we move along and use it more regularly, but there's that one. That's the quadratic model. Again, if the second differences are the same, then I have a quadratic model, and we will use our calculator regression tool at this time to find the model from it. Okay, so let's look at the next one here. Again, a recapping of the exponential model. And we know that what? If the data follows an exponential model, then it will have what we call a common ratio. Okay, between consecutive curves. Okay, so here's our little example. So I had -2, -1, 0, 1, and 2. Here's a 4, a 12, a 36, a 108, and a 324. Okay, again, the x values must be equally spaced. If they are not the same spacing, then you need to modify your values down here to make sure that it establishes and you get the right values. The common ratio, then, you want to make sure you check the ratios. So 12 over 4, that's 3. 36 divided by 12, that's 3. And you can check them all. 108, that's 3. And then the last one, obviously, is going to be working also. Over 108 is also 3. So we have a common ratio that is 3, which we also established. Let me write it differently, a little bit differently. This is our R equals 3. This is also the base number in our model. Okay? So what is our exponential model? We had this before. Okay? Depending on what you're doing, there might be slight modifications to this, but it really boils down to this. You're going to have y equals a number to start with, an initial value, and then you're going to have the common ratio to a power. I chose this one because if you can find the 0 term in here, then you want to use it. Okay? So this right here is the y value when x equals 0. This is also called the y-intercept. Okay? If I have the y-intercept, which I have right here, then use it in your model. So then my model from all this information right here is going to be y equals 36 because that's the number at the 0. And it's going to be 3 because that's the common ratio, and to the power of x. And this is the model for that table. Okay? So a couple little side notes here, just things to remember from before. What if you don't have? What if you don't have the y-intercept? Well, you can extend the table and the pattern to find it. Okay? Or you can use this rule. This is the generic we learned from exponential, from geometric series. I can use y equals a sub k, any number in the sequence. But remember that when you do that, up here in the exponent, it has to be x minus whatever that k is. So this right here is any y value. And this k right here is the x value that goes with a sub k. So I can choose one of these other points and I find this rule. But note that if I do so, there is some simplification that's going to come about. Okay? So, little note here. If you use this, then you will need to simplify. Okay? So how do I do that? Let's look at it. We're going to use the point up here. We're just going to use this one right here, the -2 and the 4. Okay? So I'm going to come over here. I'm going to use that point. So that means according to this model right here, my y is going to be the y value there, which is 4, r, which is 3, and this is going to be x minus a -2. See, it's always x minus the x value. Sorry, x minus the value up here for x. Okay, so x minus a -2, which means I have 4 times 3 to the x plus 2. Okay, so some things to remember is sometimes you can just leave this. And sometimes you can use this rule because I have that right here. So I can pull off and split it back apart. So this becomes 4, and I can write this as 3 to the x times 3 to the second. And that's a number. That's a number, see? So I can use that rule. I have that. I can split it back apart. And that number right there is 9. 9 times 4 is 36. And I can get back to this model up here that we had by solving this out over here. Okay? So this is another option available to you to get to this model right here. Okay? So these are the things you're going to be asked to do. I'm going to put a little added note in here that I want everybody to understand, some things to help you out. Because you're going to be asked to talk about, well, which one grows faster, which one goes steeper, and all that kind of stuff. Please note that the exponential grows the fastest. Then the quadratic, then the linear. So if I'm doing a graph or something like that, a line looks like this. The quadratic will look like this, and I'll just do half of it. It can come over here and do this, like that. But an exponential does this. It gets really steep. Really, the line, the quadratic, okay? The quadratic, and then the exponential is really steep, really fast. Remember from when we drew it before. So you're going to be asking questions about which one's steeper and stuff like that. That's one of the things that you can use to help you in those problems. So here's some more examples we can look at real quick. And actually, we'll do them in class. So with these examples right here, we're just going to repeat the same thing. We can do the ones in class together. So I'm in the video right here.